All right, so today we are doing the last topic in phase 4. It's called tuning neural networks, but there are a couple of things that I want to hit on today. So first, I want to talk about pre-trained networks and how you can use them to have your models perform a little bit more efficiently, or you don't have to do that much training on your own machine. I'm next going to talk about the grid search equivalent for neural networks. Talking about saving your neural network so you don't have to keep rerunning it every single time. And then I'll talk very conceptually on a high level about recurrent neural networks, which is the whole group of neural networks used for forecasting. So main applications of that include time series or anything, that's chronological, or text prediction. Text prediction is a big field where Rnns are being used as well. Okay, so to start, first we'll talk about pre-trained networks. So pre-trained networks, and specifically for CNNs, you might see it being referred to as a convolutional base. They basically consist of layers that have already been trained on very general data. So for the example of images, these layers have already learned things like general patterns, textures, colors, such that when you feed in your training data, certain features can immediately be detected, and this is called feature extraction. So we'll see some examples later on, but these networks have already been trained to recognize general things in images. Kind of similar as the concept of word embedding from before, how word embeddings that were trained on things like Twitter or Google News, they already have learned an idea of what these words mean. So kind of similar to that. So typically you can add your own final layers after those pre-trained layers to classify or regress based on your problem. This component is called fine-tuning. We're going to work through a very quick example of that. Within Keras, there are a lot of pre-trained models that already exist, which is neat. So from here, you can see these are all the already trained models. And you can sort of click into each one to figure out which are used for what kind of data. So the ones that I'll actually be going through today are called VGG. I forget if I think I have VGG 19. And this one has been trained on just a bunch of very general images. And you'll see that there are millions of parameters that have already been trained and tuned to pick out things that you would want to pick out in an image, but very general things. Cool. So to demonstrate the utility of pre-trained networks, here I'm going to show you all the performance between a baseline model and a model using a pre-trained network. So I'm actually not going to run the code because it does take quite a bit of time to run. But first you can see I have my sequential model that I'm importing, as well as my specific layers. I know, not yesterday, but on Wednesday, I didn't really talk about the dropout layer. So I'll show an example of that here. And then I'm just importing the VGG19. So the VGG19, which is a pre-trained model, all you have to do is really instantiate it and then talk about and tell Keras how you want to incorporate that into your model. So let's instantiate that first. And I'll talk about what include top means, but this is just an instantiation of VGG19. If you want to edit the input shape of your images, you can actually edit that as well. So this is the VGG19 model. You can see it's a very, very long model. There are a bunch of convolutional layers. So it's 2 convolutional layers, a pooling, 2 convolution, 1 pooling, 4 convolutional layers pooling, a bunch more of that. Finally, a flattening layer, 2 dense layers, and then making predictions. And it's 1,000 because it can make predictions on 1,000 different things. But at this moment, it's not relevant to us what these predictions are because these are not predictions for our data set. So as you can see here, this VGG19 model already has trained 143 million parameters. So this model has been trained over hours and hours and hours on millions of images, such that it has started to detect, things like textures, patterns, colors, edges, things like that. So this is another instance of VGG19. The only difference here is my include top equal to false. And if we take a look at the very bottom / top, if we take a look at the very end of this, it ends with the pooling layers. So the only difference here is this include top equal to false VGG19 model doesn't include the flatten and onwards. So ideally how we want to use this is we want this pre-trained model for its convolutional layers or for any of its 2D layers, because we want to know what it's learned that we don't have to, rescan and train our parameters from scratch with. So as you can see here, a lot fewer. I mean, this flattened layer, these two dense layers are very, very large, 4,096 nodes each. So a lot of parameters there. And because we don't have that, our number of parameters that have been trained has gone down to 20 million from 143 million. So what we're actually going to do is we're going to make use of this pre-trained model to build our convolutional neural network. Cool. So using this model, let's see how that works. Again, I'm not going to run the cells because it does take a very long time to run, but I'll just talk through each line of the code. So here we start our sequential model. Again, empty sequential model that we are instantiating. And then we will add our pre-trained layers. And all we have to do is use the .add, and it just adds all these layers. So we're just going to do CNN.add, and pre-trained is basically this VGG19 model, the one that doesn't have the dense layers. So after doing that, next what we have to do is we have to freeze these layers such that when we add our own data and add our own layers to the model, these will get changed up, because ideally these, these pre-trained layers already are trained to recognize certain things. We don't want to mess with that already learned information. So what we're doing here is we are setting the trainable or the trainability of those layers to be false. And then after that, we can add our own layer. So what we're going to do is we're going to add our own flattened layer. And just so it's quick, we're going to add one more dense layer with a ReLU activation, and then one other layer with softmax. And we can actually loop through our layers. If we loop through our layers, we can see that we have VGG19, which are not trainable. And then we have our flattened layer, our dense layer, and our next dense layer. So once we compile this model, and I actually don't have an example here because it's exactly the same as what we did in the last two study groups. When you compile this CNN model, it'll go through all of the layers, I don't know how many layers, all these 20 plus layers of the pre-trained model, not change those parameters, only change whatever the new layers that you've added are. So it's only going to train or change up the parameters of the last dense layer. Cool. Any questions on pre-trained network? The idea of using a pre-trained network and why you might want to use a pre-trained network is to save your own machine the computational power, because you won't have to start from scratch in teaching your machine how to recognize certain things. These layers have already been trained to do so. If you want to get more into it, there are a lot of different pre-trained networks, and perhaps based on what you are classifying, you might want to pick different pre-trained networks. So for example, through here, you can actually click to see what kind of data each model has been trained on. And if you do a little bit of research, you can actually figure that out as well. Cool. So that is doing pre-trained networks. So pre-trained networks exist not only for images, they also exist for dense networks. They also do exist for text data as well. Cool. So with this, you can compile and fit your model. All right, so the next thing I want to talk about is how you can do grid search using Keras. So there are two ways that you can go about this. One that is a little bit more, I guess, straightforward, but complicated in a different way. So you can actually make use of scikit-learn's grid search to do this. Now, all you have to do if you want to use scikit-learn's grid search is I've attached this, this tutorial that has you set up a Keras model to work like a scikit-learn model. And just like this, you would actually use the same syntax as you did for your last project. So here you can see all you have to do is create this function that creates the neural network, wrap it in a classifier object, and this is exactly the same as what it was before. This is basically a different way of creating that same parameter dictionary. And then you can conduct your grid search in the exact same way that you did for scikit-learn. So this way, some pros and cons. Pros, you're already familiar with scikit-learn. Some cons is that this one is it is built for machine learning models, not deep learning models. So you are storing a lot of memory, and perhaps this is not being done the most efficient way for a neural network. So the next thing I want to show you all is this library called Talus. TALOS. And I put the pip install statement over here. One thing to note for those of you who want to try this out or want to use this in their projects, because I do expect to see some form of hyperparameter tuning in your neural network projects. Talos doesn't work after Python 3.7. So I actually spent like the whole morning figuring out why Talos wasn't working on my 3.9, on my Python 3.9. So actually on Colab, the default Python is 3.7. So if you do it on Colab, it'll work fine. All right, so all I'm doing is importing Talos over here. Here I'm using the Pima Indians dataset as well, same one that we talked about on Tuesday. Yeah, Tuesday, my regular chain test split. And in order to implement Talos, let me show you how that's done. So similar to the grid search example that I showed you just a little bit before this, you want to wrap your model into a function. And the function is going to take in your X train, Y train, X test, Y test, as well as a parameter, a params function, params argument. And that params argument is going to be a dictionary. Now, in your neural network, you can tune a lot of different things, not just straightforward things like activation functions. You can also tune things like how much dropout, what metrics you might want to use, different optimizers as well. You can even use different loss functions to see how it helps if you have the option of using different loss functions depending on your problem. So the way that you do it, anything that you want to search the hyperparameters for, you will save that, you'll put that in your dictionary. So as an example, you can see, just to start with this one line. For this first layer, I want to tune the number of nodes in my first dense layer, as well as the activation function for my first dense layer. So just for these two areas that I can make adjustments, I've created a key for nodes 1 and activation 1. So nodes 1 is over here. I want to search through these 3 values. Activation 1 is over here. I want to search through these 2 values. So with that, I pretty much anything that I want to test different values for, I just make a new key with a list of different values. If I want to do the same activation function for all of my layers as an example, so let's just say for this one, which right here I have activation 2, this one I have activation 1. If I want them to just be the same, I can actually have this both say activation 1. And the downside is you either have both ReLU or both TAN-H. I have them separate because what if the first one being ReLU and the second one being TAN-H is better, or having a different, having them both have different activation functions. So that's the purpose of having different keys and values for those 2 different activation functions. So within the modeling function, you have to also have your compile step as well as your fit step. And then this is actually how Talos wants you to output your information. You want to return out, which is your model.fit, and your model object itself. So the way that you conduct this grid search is you use Talos's scan method, which is really neat. So with the scan method, you just feed it in your X train and Y train, give it your parameters, and this is that dictionary over here. Tell it what model it is, and this dense network refers to the name of this function over here. And then experiment name equal to grid. Now experiment name, I'll show you that in a bit, where this grid comes back in. The experiment name is kind of arbitrary. You can kind of name it whatever you want. If you're conducting multiple searches, hyperparameter searches, you can just call it different things. Cool. So when you run it, it'll actually show you how many iterations it's doing. So in this case, I have 3 times 3 times 2 times 2 times 2, which is 72. And it's going to run 72 different models. And here it actually shows you roughly how long it takes. So each one of these took 2 seconds. So 72 times 2 seconds, all of this is done. Now, what's really neat is you can actually pick out the best model. Similar to scikit-learn grid search, you can actually do like best estimator. Here you can do best model, and this itself is actually a sequential model. So you could do .predict or .evaluate on this over here. But what I really like about this library is it actually saves all of your modeling results to a CSV for you automatically. And also, let's just say your kernel breaks. So even on Google Colab, you do have like a disk limit. So as you can see over here, oops, why is this like this now. As you can see over here, I'm using like a little less than half of my disk space. I'm using 37 gigabytes of space. And I'm also using like 1.4 gigs of RAM. If you're running something very, very heavy, like image data, you can actually sometimes hit the Google Colab limit. So what's really nice about Talos is, let's just say you go through half of your iterations, it's actually saving your results of each iteration to a CSV. So if for some reason it stops at iteration number 30, my CSV, which is saved over here, and I'll show you all what this is all about, it'll actually save the 30 results. So you don't have to redo the 30 results again, which is really neat. So I like Talos a lot for that reason. So I can just read CSV, and as you can see here, it comes out of the grid folder. And this is actually a timestamp of when I ran this. And this is just earlier today, which is why you see September 3rd. Sort my values based on validation accuracy. And I can see what the best model is. So from here, you can see that my best model is both ReLU activation functions, a dropout of 0.1, 100 nodes, and an SGD optimizer. Now, this is kind of specific to Google Colab, but in Google Colab, you can actually see your table of contents over here. Actually, let me pull down this bar. There you go. So you can see your table of contents here, but if you click this over here, you can actually reach your files. So right now, this is just stored locally. If you mount your Google Drive, you can actually have all of this save automatically onto your Google Drive, which is really nice as well. Cool. Any questions on this hyperparameter tuning? All right, I've also linked another Talos walkthrough. Oh, question?
I was just wondering if you could add anything else to it, or is that the only things that we could add to it? Like, for example, could we add like L1, L2 as a parameter?
Absolutely. So you know how within each layer you can say like, I think it's like regularization equal to whatever. You can actually turn that into like a key. You can turn that into a key. And if you want to search different values of regularization, you can do that here as well. Yeah, so these are actually very, very flexible as long as you can represent their values in a list of values, and as long as you can put like a dictionary lookup within the model function, you'll be good. Next, anything else?
If you go all the way a little bit more up where you build the model under the definition, there's a under out, you have a verse boss equals 0. What does that stand for under model fits?
Good question. So verbose equal to 0. You know how when we ran our models last time, let me see, first neural network is what it was called. So when I ran the models last time, it had this output over here. So this is verbose equal to 2. So the bigger the verbose number, the more information will be output. Because this is running like 72 different models, I set verbose equal to 0 such that all of those things won't be printed out. But you could technically set verbose equal to 1 or 2 such that each model's like training process will be printed out. Because for this, it's only like this. If you won't see like the per batch per epoch training for each model. Yeah, and also, awesome. By the way, since, oh, you're welcome. From this, you can also tune the number of epochs in your model. You can tune the batch size as well.
Just add them to the dictionary, basically?
That's right.
Oh, wow. Okay, awesome. So you could do it all one step and you don't have to do anything after.
Absolutely. Yeah, pretty much. The only thing that you can't really change is like the structure of your neural network. So for example, there's not really a way to say, okay, I want to have 3 dense layers in one model or 4 dense layers in one model. Like completely having new layers, it's not, I don't think you can do that with Talos.
Okay, so the other thing I wanted to ask, so instead of dense, could we incorporate CNN as well, or does it have?
Absolutely, 100%. You can definitely do CNN layers and pooling layers as well.
Awesome. So we could do whatever kind of structure we want, and then the parameter, we could do it all in one step. Awesome. Thank you.
You're welcome. Yeah, Talos is a really, really neat tool. The only downside is, not optimized for Python 3.9 yet. But I mean, I think most of you, especially those of you who are using the Learn environment, you'll be fine here. All right. Anything else about hyperparameter tuning? Again, I have a Medium walkthrough over here. This is just someone walking through things that they've tuned, and they're doing it for a CNN model as well. So you can see here, they have their model there with their CNN layers. Cool. Let me close this out. All right. So next, real quick, I want to talk about saving your model. Especially if you're dealing with image data, sometimes one model can take very, very long to run. I remember my phase 4 project, especially when I ran Talos with it, I basically left my computer running for at least 6 hours. So you don't want to go through that process again and again. So it's always good to, like, right after you run your like grid search or whatever, save your model. And so here I just have like a really simple model that I built. And oh man, let me see if I can run this one. This should be pretty quick. Let me make sure I have all my imports first. Okay, with these imports, let's go down to, I don't want to rerun that grid search. Okay. Oh, I know what it is. Okay, cool. So this is training my model, and this is the Pima Indians data set again, so it should be pretty quick. So this model is running, should be done in just a couple seconds. All right, now that that's done, we can get our metrics. All right, let's get those metrics. There we go. So these are our metrics for the data set. And let's just say, okay, at this point, I'm really happy with my model. I want to save this model to be used like in a different notebook. If I want to productionalize it, we can talk about that more during the capstone phase 2. Or I just basically want to save this model so I don't have to redo this training process all over again. Of course, this data set is much, much faster than using an image data set. To do that, you have to save 2 things. You have to save your model and its architecture. You also have to save all of its parameter weights or its parameter values. You have to save both of these. If you save your model without the weights, you'll basically have to retrain your model from scratch. Kind of defeats the purpose. So you do have to save both of these. And the typical extension, file extension is H5. I honestly forget what H5 stands for, but that's the typical Keras TensorFlow model extension. So with this, we are saving model.h5 and model weight.h5. So within Keras, you can just load up that model really, really simply. Load model, load your model. And then from the model variable, you want to load in the weight. So it's just these 2 lines to load up your model, either in a separate notebook or just somewhere else. And that will work. So you can see I can run this evaluation off of my model, which was only created over here. So technically this code could be in a separate notebook. It'll work fine as well. So these lines of code, surprisingly hard to find on Google, which is why I just put them right here. And as you can see, it automatically saved these 2 as files in my repository. That was a quick one. Any questions about model saving? You could technically also pickle a model, but I have seen instances where the pickle cannot handle all of the weights and the pickle file ends up being too big. So using Keras's built-in save functions are a little bit safer in my opinion. Okay, I'm going to next go through a quick slideshow on recurrent neural networks and how those work. I've linked some implementation examples over here in case you want to implement your own RNN or any sort of forecasting model using a neural network for your capstone. And if you're doing the time series project for this project, you could do this as well, although definitely not required. So here are some examples for implementation. I'm going to just talk about some concepts related to RNNs. Cool. So recurrent neural networks. The thing that's unique about recurrent neural networks versus sequential dense networks is it's sequence learning. So you're not just looking at a set of data points. I mean, it's very, very similar to as to why time series data is different from regression data. It's because sequences matter. Like ABC will produce a different outcome from ACB, right? If you're thinking about, I mean, right now what's very hot is looking at stock market data, especially with like all of those like crypto things that are going on right now. The order of your data points does matter. And that's something that our current neural networks, the ones that we talked about so far, regular dense networks, as well as CNNs, don't really account for yet. So several considerations. How can every element be represented numerically or a vector, and also sequence length? Is it variable or is it constant? These are things that you want to think about. So for example, for things like text prediction, for making predictions on some words, you might not need as many preceding words to make that prediction, if that makes sense. If you know the context of what you're talking about, let's say, for example, like what's that text autocomplete? When you're like completing, I think now they actually tell you like what they think your next word is going to be. If they have some context of like, it's 7 p.m. Where are you? We're at dinner. You need like however many words preceding that versus some other scenarios, you might need a lot more or less context. So for text prediction, it's actually really, really interesting as well. Cool. So some examples of actually what technologies use Rnns. So frequent pattern mining. Things like checking out n-grams in word embeddings actually do use some form of RNN. So for example, how word embeddings are able to recognize phrases, commonly used phrases, as well as idioms, or actually phrases and idioms, any length of words that often occur together, uses some form of sequence learning RNN. ARIMA, if you were to expand ARIMA to include many, many terms, it can actually start to look like a recurrent neural network, because ARIMA is looking at past patterns of past occurrences of patterns. So very, very similar. If you were to really scale up ARIMA modeling, it can look a lot like a neural network. Markov models are more probabilistic, and sliding window models, which is literally what is the technology used to generate word embeddings. These are all examples of sequence learning. All right, so why isn't a multi-layer perceptron enough? And multi-layer perceptron is another word for just our regular dense neural networks. So let's think of a simple example of univariate time series. Why is an MLP not enough? So first, if you think about the input shape of your time series data, a lot of time your input shape is not going to be quite variable, because sometimes you have X number of rows before, sometimes you have Y number of rows before, but you want it to be able to recognize different lengths of time so that it can figure out, okay, where am I going to pick out patterns? So inputs won't make very much sense unless you have some sort of very systematic way to scale them. And it's very, very prone to making poor forecasts. It's as if you wanted to run a regression model to do time series forecasting. So to think about why recurrent neural networks kind of improve upon that, a regular forward feed neural network, so an MLP, have an activation function that is fed in all the inputs and then goes into the output. So the direction of data flow, I mean, yes, backpropagation goes backwards, but it's only going fully forward pass or fully backward pass. Recurrent neural networks do it slightly differently. They have an activation function that is also forward propagated and is fed from the output of the previous step in the sequence. So before making a full forecast, it actually runs its data backwards. So it can take a look and see, all right, this prediction that I'm trying to make, how does this compare to the predictions that I was making prior? Recurrent neural network is also an umbrella term for other models like Lstms, which we'll talk about very, very briefly later. GRUs, actually GRUs is a couple of readings in your appendix, I believe. But yeah, cool. One other thing to note in terms of activation functions, for some reason for recurrent neural networks, hyperbolic tangent activation function for some reason has always outperformed everything else, even ReLU. So in terms of activation functions, tanh is always good. It's useful because it can also go positive and negative to take into account absolute changes in values. Okay, so if you're thinking about RNNs, there are actually a lot of different ways to think about RNNs. I think that this part, if you think about things like different applications of RNNs might use different RNN structures. However, when you're implementing it, you actually don't have to think about it this way, but useful to conceptualize, I do think. So to take some quick examples, one-to-one. So one-to-one is sort of like univariate time series. We look at the day before to make the prediction for tomorrow, as an example. Many-to-one is very, very similar to what's being used in text prediction or any sort of sequential recommendation system. So in terms of text prediction, yes, you're looking at many words from before to come up with the next word. And then this next word is then fed into this many input to come up with the next word. Also sequential recommendation systems. If you think about Spotify recommend playlists, how playlists are generated as an example, maybe you put like 10 songs in your playlist, and I think on Spotify, they actually can tell you, all right, we think you should add this to your playlist. So that's an example of sequential recommendation system, which does use a many-to-one structure. The rest of these, I mean, you can spend some time thinking about the different applications of this, but not the most important thing, especially for right now. Cool. Some other applications of recurrent neural networks, again, as I mentioned for NLP, predictive text, as well as sentiment analysis. Again, doing RNNs within sentiment analysis, you are taking into context the sequence of words. For recommendation systems, you can use RNNs for collaborative filtering if you treat things that people have rated as a sequence of things that they've rated. This actually helps to take into account of people's changing tastes over time, which is really cool. As well as content filtering, though it's not a very common use. Multivariate time series forecasting, that's actually very similar to, that's actually a use of many-to-one as well, if you're using multiple things to predict one outcome. Also, audio interpretation has used RNN because audio is sequential as well. Image recognition, you could do that for videos as well. CNNs tend to do better though, because you can do recurrent CNNs, which is very, very heavy. I don't think most of your computers can handle recurrent CNNs, but it is possible to do recurrent CNNs, which is wild. Okay, so the way that you think about an RNN, and actually this comes from a really, really good deep learning course that I think I have linked at the end of this slideshow. When you're thinking about RNNs, you are keeping track of a lot of states. So for example, if you have multiple RNN cells, and you can think of a cell as a layer, when you have an input, you have to consider its prior states at each layer, and use that information to make predictions on your current state. So this will take a little bit of getting used to. I will actually at the end, actually next week, no, the week after you finish your projects, I'm going to send out a whole list of resources that are really good to look into post-graduation. This is one of them. All right. So before we get into coding, let's think about how recurrent network works input-wise. So oftentimes a lot of our data looks like this, right? If you have a bunch of words, and actually really interestingly, if you're looking at very advanced autocomplete or text generation projects, they actually store their input and output data as letter by letter versus word by word. Reason for that is actually really interesting. If you think about it, it probably would make more sense to us. If we were trying to predict if we're doing some sort of text prediction, it makes more sense to think about the words used before. But for a computer, because there's so many unique words and not as many unique letters and characters, computers have actually learned, or it's a lot faster and more efficient for a computer to learn text letter by letter, especially if it's looking at it via a sequence. Because of that, it will almost never create a word that isn't in the dictionary, which is really cool. Cool. This is actually covered in the walkthroughs that I sent out, so I'm not going to go into much detail here. Cool. So for code, you can use Keras to implement. You can use pretty much all the same things. Just the layers, the RNN layers are the ones that are different. All right. So for LSTM specifically, so LSTMs are a subset of RNNs, and LSTMs are actually the ones that are I think they're the current industry leader in doing stock predictions. And LSTMs basically stand for long short-term memory. It basically has variable lengths of memory as to like how much context do you need to make the next prediction, which is very cool. So if you're thinking about predictive text, take this sentence as an example. There is a castle in the mountains on a river across from the valley where the king's army was marching. So king's army, army marching, those connections are very, very obvious. However, castle to king, there are so many words in between the words castle and king. But if it wasn't an LSTM, there's a chance that this model would have forgotten that connection, because if you don't have this variable memory length, there is no way to account for that. There's no way to be like, okay, well, this sentence seems to have a lot of filler words, so there's no way to tell a regular recurrent neural network that. So this is what LSTM accounts for. I'm going to show you all a kind of complicated diagram next, but basically within an LSTM, what allows it to remember, or what allows it to play on different lengths of memory, is the combination of a forget gate with their input and output gates. So basically, another parameter that it's going to be tuning is what information are they going to keep or throw away at each point of time, given new data that is streaming in. It again becomes very, very complicated mathematically, but you can sort of think of it as, okay, it's making a judgment call as to how much information to retain at any one time, because you at the same time don't want to retain information from like 100 words back or maybe 5 sentences back. But sometimes that is important as well, depending on the context. And that's something that an LSTM can pick up on. So yeah, vectors are going into all of these gates, and they all have weights and biases associated with each of them, which are learned in the backpropagation process. All right, so to just summarize, GRUs is covered in your appendix. It's a good thing to read. And there's also bidirectional Rnns. Bidirectional Rnns basically can update predictions that were made prior. So if you're trying to forecast like a year in advance, based on the future predictions, it could possibly go back and be like, okay, maybe my predictions for days 5 to 10 don't really make sense, which is cool. And here are a bunch of resources. The Coursera course by Andrew Ng is really, really good for deep learning. It is like the go-to deep learning course. And then there are a bunch of other videos these are a bunch of resources put together by an instructor that does specialize in Rnns a lot more than I do. So highly recommend those resources as well. But yeah, Rnns is like a whole nother beast of neural networks, just because it is very structurally different from the way that we would think about regular ML, multi-layer perceptrons or convolutional neural networks. So yeah, at this point, we definitely don't have to implement any, but you might want to include some form of an RNN in your capstone, though it's optional. All right, any questions? Cool. Well, if there are no further questions, you all go back to work on your projects. Let me stop this recording over here.